Assalamualaikum Dr. Habibullah and everyone. My name is Nur Fatiha binti Zulkifli and my number metric is 293484. Today I will be presenting my individual assignment. The topic that I have chosen is integral calculus of function of several variables. So in this slide, I will talk about introduction, that is the explanation about the topic, theories and law, demonstration example, the solution on how to solve some questions, and lastly the conclusion. So in this introduction, I will explain about integration. Integration is a fundamental concept in calculus that involves finding the antiderivative of a function. It is the reverse process of differentiation and provides a way to calculate the total accumulated change or area under a curve. The results of integration is called an integral, and it is represented by the symbol integrate. The function being integrated is called the integrand, and it is written next to the integral symbol. The integrand specifies the rate of change of a quantity, and integration allows us to determine the quantity itself. So next is multiple integrals. Multiple integrals extend the concept of integration to function of multiple variables. While a single integral deals with a one-dimensional scenario, multiple integral allow us to integrate over two or more dimensions, taking into account of interaction between variables. The most common form of multiple integral is the double integral, which involves integrating a function of two variables over a region in the xy plane. It is denoted by double integral or placing two integral symbols consecutively. The limits of integration are defined for each variable, specifying the region over which integration occurs. The general form of a double integral is double integral fyx dA. Here, fyx is integrand representing the function being integrated, and r is the region of integration in the xy plane. The symbol dA denotes the differential area element, indicating that the integration is performed with respect to both y and x. For the next slide, I will talk about application of multiple integrals in real life. Multiple integrals have numerous real-life applications that impact various aspects of our daily lives. Here are some examples. For the first one is engineering and architecture. Multiple integrals are used in structural analysis to determine the moments of inertia and centroid of complex shapes, which are crucial for designing beams, columns, and other structural elements. They are also employed in fluid dynamics to analyze fluid flow patterns, pressure distribution, and heat transfer in systems like pipes, channels, and heat exchanger. For the second one is environmental science. Multiple integrals are applied in environmental modeling to study the dispersions of pollutants in air and water. By integrating over three-dimensional regions, scientists can estimate the concentration of pollutants in a given area and analyze their impact on ecosystem. And for the third one is computer graphics and animation. Multiple integrals play a vital role in computer graphics and animation. They are used to stimulate the behavior of light as it interacts with surface, enabling the rendering of a realistic image with shading, reflection, and refractions. Integrals are also employed to calculate the area of object and surface, which is crucial for collision detection and object interaction in simulation and game. Let's move to theories and law. The first theory is double integral over rectangle. The double integral of f over the rectangle r is double integral of fy dA equals limit mn approach infinity sum of m to I equals to 1 and sum of n j equals to 1. fxi yj multiple area of A. If this limit exists, this is called a double Riemann sum. If fyx more than 0, then the volume V of solid that lies above the rectangle R and below the surface Z equals to Fyx is F double integral Fy dA. For the second theory is Fubini's theorem. Let Fxy be a continuous function defined over rectangle R equals AB multiply CD. Then the order of integration does not matter, and so double integral Fxy dA equals to double integral Fxy dx limit BA dy limit dc equals double integral Fxy dy limit dc dx limit BA. More generally, this is true if we assume that f is bounded on R, f is discontinuous only on a finite number of smooth curves, and the integrals exist. So here are some examples for our topic. The first question is, estimate the volume of the solid that lies above the square R equals to 0, 2, multiply 0, 2, and below the elliptic paraboloid Z equals to 16 minus a square minus 2b square. Divide R into 4 equal square and choose the sample point to be the upper right corner of each square R. Sketch the solid and the approximating rectangular boxes. For example 1, we know from the question that it is a square. Now I'm going to do the graph to show how it looks like. So now we divided our square into 4 equal square. We know from the question that the square is 0 to 2. Now we got 4R, that is R11, R12, R21, and R22. The question asked to choose the sample point to be upper right corner of each square, so we got 1, 2, 2, 2, 2, 1, 1, 1. Now I'm gonna rewrite our equation. So now R11 equals to area A1 multiply area B1 equals to 1. This also applies to R12, R12, R21, and R22. For the sample point, we know that F11 equals to 13 because we substitute F11 into the equation 16 minus a square minus 2b square. So that also goes for F12 equals to 7, F21 equals to 10, and F22 equals to 4. Approximating the volume by the Riemann sum with m equals to n equals to 2, we have sum of 2i equals to 1 and sum of 2j equals to 1, f ai bj area ai multiply area bj. Sorry for my mistake, that is not y, it's b, so area bj equals to f1 1 multiple area A1 multiple area B1 plus F12 multiple area A1 area B2 plus F21 multiple area A2 area B1 plus F22 multiple area A2 multiple area B2. So now we know that F11 is equals to 13, so 13 multiply 1 because area A1 area B1 is 1, so by substituting in, we got 13 plus 7 plus 10 plus 4 equals to 34. Therefore the answer is 34 units cubed. These are more examples of multiple integral. Reminder, when fx is a positive function over a rectangular region R in the xy plane, we may interpret the double integral of f over R as the volume of the three-dimensional solid region over the xy plane, bounded below by R and above by the surface. Z equals to fxy. And for example 3 is finding the volume of the prism whose base is the rectangle in the MN plane bounded by the M axis and the line n equals to m and m equals to 1, and whose top lies in the plane Z equals fmn equals 3 minus m minus n. Example 3. We know from the question Z equals to fmn equals to 3 minus m minus n. So So, reminder, we know from the previous slide that volume equals to double integration fxy dA. I'm gonna write it on the top right. So we know that n equals to m and m equals to 1 from the questions. I'm gonna write the graph here. So that's 1 and 1. And I'm gonna highlight the area region here. So now we will substitute our equation to our formula, which is double integral 3 minus m minus a dA. From the previous slide on the theories and laws, we know that we can use Fubini's theorem on this equation. That is double integral 3 minus m minus n dm dn, or double integral 3 minus m minus n dn dm. We can solve it now. To solve double integral, we have to solve the first integral. I'm gonna use the below one, that is double integral 3 minus m minus n dn with the limit m 0 and dm with the limit 1 0, because we want to integrate the variable first, so we can have the exact value. Now we're solving the integral 3 minus m minus n dn with limit m 0, that is equals to 3m minus m square minus m square over 2. After we integrate it, and we got the final answer, that is 3m minus 3m square over 2. Okay, now we have integrated the first integral. We have to integrate the second integral by substituting the new equation into the integral. Sorry for my mistake, that is not dx but dm. So now after integrating the second integral, that is equals to 3 over 2 minus 1 over 2 equals to 1. Therefore, we have the final answer, that is 1. In conclusion, multiple integrals are fundamental concept in mathematics with wide-ranging application in various fields. Throughout the video, we explore the key aspect of multiple integrals, including their definition, notation, and integration technique. We discussed the significance of multiple integral in calculating volumes and area. We also highlighted their role in engineering, computer graphics, and environmental science. Multiple integral have practical application in engineering design, environmental science, computer graphics, navigation system, medical imaging, economics modeling, and much more. They provide a powerful tools for analyzing and solve real-life problems that involve multiple variable and complex systems. To further explore the topic of multiple integrals, it is recommended to study advanced techniques such as change of variable, iterated integrals, and application in vector calculus. Understanding this concept in depth will enhance your problem-solving abilities and open up new possibilities for research and application in mathematics and related disciplines. By delving deeper into multiply integral, you can unlock the potential of innovation and gain a deeper understanding of the mathematical foundations that underpin many aspects the world we live in.